Hi everyone. So most of this video will basically just be describing or giving conceptual examples of rules and properties derivatives. So if you already understand these concepts thoroughly, I do recommend that you just get close to the very end where we have a summary of everything you need to know and everything I think that's covered in class on this day. So to start though, say we have y equals to some constant c, where c is any number. It can be either 42, it could be some extremely high number, it could be any number really. Then the derivative of c, or derivative of y, is 0. So looking at this graph, if y is equal to some number c for all x, then it can be depicted as a horizontal line. And the change in this horizontal line, or the change in y or the change in x of this horizontal line, is always 0, because there's no change in y. So the second rule they teach you is that if y is equal to x, then the change in y, or the change in x, over the change in x, is always equal to 1. So, well, if you want to look at it somewhat algebraically, though I'm not sure if this actually, well no, this does work. If y is equal to x, then rather than have change in y over change in x, I can just write change in x over change in x. And naturally we know from algebra that anything divided by itself is always equal to 1. And as you can see from the graph, it doesn't have to actually pass through the origin, because what we're measuring is the change in y or the change in x. So it doesn't matter what y is at any particular point, because all we're measuring is a change in that value. Okay, so the next rule is that if y is equal to x to the nth power, then the derivative of x to the nth power divided by, the derivative of x to the nth power is equal to n times x to the n minus 1th power. Okay, this is a bit harder to grasp conceptually, but describing graphically would probably work fairly well. So assume this parabola is a function of f of x is equal to x squared. Then the derivative of x squared should be, according to this rule, 2 times, or 2x to the first power, because I'm bringing the 2 down, and I'm reducing the 2 by 1 in the exponent. So I get 2x is the derivative of x squared. So say this graph shows 2x. Okay, so let's compare our two graphs. In our original function, we have f of x decreasing rapidly. So the derivative should be originally very, very negative, because it is in fact decreasing by a huge amount. And we do find the derivative is negative and very negative in the derivative graph, or in the graph for the derivative. However, as we get closer to the apex, we find that the graph levels out, and at this point it seems to have no change at all. So it becomes 0. And that's what we see in this graph as well. It decreases less and less each time where it starts to flatten out, before the change in the original function finally becomes 0. And then we see it increasing slowly, and then it starts to rapidly increase. And we see the same thing here. The derivative is slightly positive, so that means there's going to be small increases in the original function. But as the derivative gets larger, there's a more rapid pace of increase. So hopefully that does give you a good idea of why this rule seems to be true, though an example doesn't necessarily work. If you're really interested in the mechanics of this particular rule, I would in fact look it up on Google. Though that's probably not good advice. It would probably work in this case. Okay, so you're also given two very important trigonometric rules. If y is equal to sine x, then the change in y over the change in x is equal to cosine x. So the derivative of sine x is cosine x. Likewise, the derivative of cosine x is negative sine x. Okay, so describing these pictures and comparing them graphically would probably just be very confusing and somewhat of a waste of time, so I'm going to leave this to you to try to memorize. If you're looking for patterns, I do recommend that you try to find them yourself, though I may try to give you patterns at the end of this video. But honestly speaking, since we only have two examples so far, there is very little to go on, but I would try to memorize these. Okay, so the next rule, or this is actually the property of derivatives. So say you wanted to find the derivative of f of x plus g of x. Well, the derivative of that is the same thing as the derivative of f of x plus the derivative of g of x. So say I have the function f of x is equal to x cubed plus 1. Well, I know what the derivative of x cubed is. It's 3x squared. And the derivative of 1? Well, 1's a constant, so the derivative of that is 0. So you find the derivative of this entire function to be simply 3x squared plus 0. Also, I want to make a clarification. I know I just had the addition sign here, but this also works with subtraction. So if I wanted to find the derivative of f of x minus g of x, well, that's the same thing as the derivative of f of x minus the derivative of g of x. So you could also imagine it as adding the negative of g of x, if that maybe clarifies things. Okay. Also, this is, I think, explicitly mentioned in class. But if you have a function that's the product of two different terms, then you want to expand the function before you differentiate. Especially because at this current moment in time, we don't, or as far as you know, we don't have any rules dealing with multiplication of derivatives, multiplication of terms. You want to get it so that you have individual terms that you can isolate. So x plus 2 times x minus 2, well, using FOIL, that's x squared minus 4. And if you want to find the derivative of that, it's just using one of our rules, 2x, and then this just becomes 0. So derivative all in all is just 2x minus 0. Okay, so the last property of derivatives is that the derivative of a constant c times f of x is equal to that constant times the derivative of f of x. So say I have the function y equals 5x. Well, I know the derivative of y equals x is 1. And I know 5 is a constant. So the derivative of y equals 5x is just 5 times 1. Or just 5. So it actually sums up everything you need to know, everything you've learned from today's lesson. But important things you want to remember. You want to memorize the rules. You definitely want to memorize the trig rules, because that will definitely bother you during test days. If it looks relatively easy to derive, and you could probably derive it in class if you needed to, but that would waste precious time, and I assure you that there are very few students, if any, that have finished the calculus test before the bell rang. So I do recommend that you spend the time to memorize these rules and properties and these trig rules. And of course, you want to memorize these properties. So thank you, hope calculus is a blast, and have a nice day.